Hi everyone, this is Kalyan Kumar and welcome back to Chemistry Universe. We've already done part 1 of alkanes, then we did organometallics, and this is part 2 of alkanes, in which we're going to discuss the physical and chemical properties of alkanes. So basically, we'll first look at the physical properties of alkanes, their boiling points, the trend of their melting points. We'll talk about their solubility. We'll talk about how branching changes boiling and melting points, and we'll talk about how many of them are gases, solids, and liquids. And then we'll talk about some important chemical properties. But as I said in the introduction of alkanes are the ones which have very less affinity. We call them as paraffins. And the very act of doing that is to tell you that they have less affinity. And therefore, alkanes are not going to show you that many reactions. Some of the reactions are important, especially halogenation, isomerization, and so we'll do some of those in detail. There are certain other reactions which do happen, but we have no practical use for those, but we'll still discuss that. So let's get on with the show, and we're doing physical and chemical properties of alkanes. All right, so let's get the ball rolling. So we'll start with the physical and chemical properties of alkanes. Now, the first four alkanes, that is methane to butane, are colorless gases. Neopentane, in fact, is also a gas. The next 13, that is pentane to heptadecane, are colorless liquids, and those containing 18 carbon atoms or more are solids at ordinary temperatures. Now, this is relatively easy to understand because as the molecular mass increases, the surface area increases, it is much more easier to polarize these molecules. Remember, the forces of attraction between these molecules are LDF, London dispersion forces, and they are very weak forces. And all of these weak forces are called van der Waals forces, and out of which LDF is a pretty weak force. Now, LDF is basically an induced dipole kind of an attraction, and so inducing a dipole in a molecule which doesn't have one requires polarization. And bigger the size, the easier it is to polarize. And therefore, as you go higher in molecular mass, you'll find greater intermolecular forces of attraction, which leads to more condensed states. We go from gases, then liquids, then solids. Now, boiling point of alkanes increases as the number of carbon atoms increases. For a given alkane, the boiling point decreases with the increase of branching in isomers. This is because of decrease of van der Waals forces. And as I said, boiling point is directly related to molecular mass. Remember, it's not directly proportional to molecular mass, it is directly related to molecular mass for all the very reasons that I told you why you have condensed state of alkanes as the molecular mass increases. And therefore, more the molecular mass of a liquid alkane, more would be its boiling point. And that makes sense because higher molecular mass means greater surface area. Greater surface area means greater van der Waals forces. And obviously, as branching occurs, the van der Waals force will decrease. You see, what branching does is branching actually is going to make the molecule more spherical in shape. Now, for example, let's take an example of a sheet of paper. Now, the sheet of paper, as you hold it like this, its surface area in the front and the back is exposed to other molecules. But if I fold this into a cylinder, you'll find that the inner surface area is gone now. It's not exposed. Only the external surface area is exposed. So the surface area of a molecule decreases on branching. And as the surface area decreases, so does boiling point. And I'll just show you how the boiling point varies with branching. So here we have a graph between boiling point and number of carbon atoms. And as you will notice, this red graph tells you the boiling point of N alkanes. And as you can see, as the number of carbons increases, boiling point increases. Of course, it doesn't increase in a straight line, and we don't expect it to do that. But if you look at isoalkanes, the boiling point of isoalkanes for the same number of carbon atoms are less. They have similar trend, but isoalkanes do have lesser boiling point than others. And regarding what isoalkanes are, well, for most of the alkanes, except of course octane, if you have an alkane like this is a normal alkane, right? In the second position, if you have a methyl group, that's called an isoalkane. Define an isoalkane, all you need is straight chain alkanes. On the second carbon, you have a methyl group, no other branching. That would be called a isoalkane. Except for octane, where it is 2, 3, 4, 5. Except for octane, where this is called isooctane, this blue graph is actually meant for these kind of alkanes, where you have a 2 methyl on the second carbon. Now here there is a little difficulty in understanding melting point. Now melting point is something which increases as the molecular mass increases, makes sense. But there is a bit of a weirdness to it. When you go from let's say C19 or let's say C18 to C19, the boiling point, the melting point will increase. But when you go from C19 to C20, the melting point increases more. So the rate of increase of melting point from 18 to 19 is less. The rate of increase of melting point from 19 to 20 is more. Melting point increases every time as you increase the molecular mass. But the rate of increase from even to odd is less than from odd to even. This has mainly to do with symmetry. You see, even numbered atoms have greater symmetry. In fact, not only even numbered atoms, atoms with even numbered similar atoms are more symmetric than others. And more is the symmetry, better is the packing into a crystal lattice. Better is the volume of the atoms inside a unit cell that makes it have a higher melting point. Better the packing, better will be the melting point. So melting point also increases as the number of carbon atoms increases in alkanes, but the change in melting point is not as regular as in boiling points. When we go from an odd numbered carbon atom alkane to the next higher even numbered carbon atom, the melting point increases more when we go from even to odd. This is because of more symmetry in solid crystals in even numbered carbon atom alkanes. Now, molecular symmetry determines the packing coefficient or packing efficiency in a crystal, which is the ratio of occupied space to the free space in a crystal. Higher the packing coefficient, more the number of molecules in a unit cell, and hence higher the melting point. Now, you must have done this in solid state, or if you haven't, you will do it in solid state. There is something called packing fraction. It is a fraction of the total unit cell space that is occupied by the atoms. And better the packing efficiency, better the packing, more will be the melting point. And even numbered ones have definitely more packing. Molecular symmetry in our context can be measured in terms of number of chemically different carbon atoms in the given structures. For example, benzene has 6 carbon atoms, that is even, of one single chemical type. That's the best part. Unlike toluene, which has 7 carbon atoms in 5 chemically different types. 1 methyl, 1 ipso, 2 ortho, and 2 meta, and 1 para. Hence, we can say that benzene is more symmetric than toluene. So, when it comes to melting point, boiling point of toluene could be higher because of higher molecular mass. But when you look at, this is benzene, right? So, you have 6 carbon atoms, all of chemically similar nature. But if you have a toluene, you have 1 methyl group of one type, 1 carbon where the methyl stands, which is unique, 2 are ortho. These 2 positions are called ortho. So 2 of them are ortho. These 2 positions are called meta. 2 of them are meta, and this one is called para. So there are basically 2, 4, 6, 7 chemically different types of carbon atoms. And that makes the 7 carbon atoms, which are 5 chemically different types, one methyl, etc. That makes it have lesser symmetry in toluene than in benzene. And of course, where intermolecular forces are not too strong, like H bonding, molecular symmetry plays an overwhelming important role. Of course, if you have a very strong intermolecular force like hydrogen bonding, then irrespective of whether it is symmetry or non-symmetry or even or odd, it will have a higher melting and boiling point. But when you don't have those forces, then symmetry is the one that would decide the melting point. So melting point of alkanes go in this order. Increases. This is see the increase, and this is carbon number 3, third carbon atom, then fourth, then fifth, and sixth. You can see 3 to 4 rise is rapid, whereas 4 to 5 is not that high. Another thing that is important is branched alkanes are more spherical and are therefore better packed in crystal lattice. Their melting point is greater than that of straight chain alkanes. Now, I've already told you that boiling point decreases with branching, while melting point increases with branching. Boiling point decreases with branching because as branching occurs, it becomes more and more spherical. More and more spherical, lesser surface area, lesser van der Waals force, lesser boiling point. In melting point, more branching means more spherical in shape. More spherical in shape, better symmetry. In fact, the three-dimensional shape which has the maximum amount of symmetry is a sphere. It is completely spherical in all directions. So you draw any diameter, any line passing through the center of a sphere, that would be as symmetrical as any other line passing through the center. So more spherical a molecule gets, more would be its symmetric, and therefore more would be its melting point. So melting and boiling points go in the opposite trend as far as branching is concerned. So boiling point of this, and this, it decreases. Whereas when it comes to melting points of these, it increases from left to right. Now, alkanes, as you know, are non-polar, and so they dissolve only in non-polar solvents like CCl4, benzene, etc., and not in polar solvents like water and alcohol, and that I'm sure is understandable. Now, another important feature of alkanes is density. The density of alkanes increases as you increase the molecular mass. Now, what happens is that density increases, but it reaches a peak value at C16 of 0.8 gram per ml. And that's the peak value. So after that, see, the fact that density is increasing as you increase molecular mass means the increase in mass is overcoming the increase in volume. But it reaches the peak value at C16. After that, the increase in mass is being compensated by increase in volume. So 0.8 gram per ml is the maximum density of any alkane. And therefore, all alkanes will float in water. And I remember there was one particular question in JE where they said cyclohexane floats in water because. And one of the options given was the boat form, cyclohexane exists in boat form. Now we have already done isomerism. And you will notice cyclohexane does exist in boat form, though not the maximum amount of cyclohexane. But the fact is that is not the reason. Just because it's a boat form, it doesn't float. It floats because its density is lower than that of water. Alright, now let's look at the density of alkanes show a definite rise with increase in molecular mass, but they reach a limiting constant of 0.8 gram per ml with C16, and therefore alkanes are lighter than water and float in water. Now let's look at chemical properties. Now the most important chemical property is halogenation, a part of which we have done in the case of alkyl halides. Now chlorination may be brought about by photoirradiation, heat or catalyst, and the extent of chlorination depends largely on the amount of the chlorine used. And this is pretty obvious. You have an alkane, you have chlorine. If you have a limited amount of chlorine, you will get monochloro. Chlorine is a little more, you get a dichloro and a trichloro, and depending on the amount of hydrogens available in the alkenes, you'll get that many chloro compounds. So you'll get a variety of these compounds. So if you want only monochloro, then keep the alkane in excess. So let's say ethane, for example, you do H nu or heat in the presence of Cl2, you get monochloro. Now, bromination is similar to chlorination, but it's not that vigorous. Iodination, in fact, is reversible, and it may not, but it may be carried out in the presence of an oxidizing agent such as HIO or HNO3, which destroys the hydrogen iodide formed as it is formed, and so drives the reaction to the right. You see, what happens is that whenever you get halogenation, one H of alkane goes away and one halogen comes in its place, and that hydrogen goes with the other part of the halogen. Like say, for example, ethane with Cl2, one H will go and one Cl will come, and this H will go with the other Cl to form HCl. Now, when it comes to iodine, you get HI, but the reaction is reversible. So, how do we make the reaction go forward? We oxidize the HI using compounds like HIO and HNO3. So, HI is removed from the system, and as it is removed from the system, the reaction will go forward. And direct fluorination is usually explosive, so special conditions are necessary for the preparation of the fluorine derivatives of the alkanes. Let's look at the mechanism. The basic mechanism we've already done. We've done the chain initiation step. Chlorine molecule breaks in the presence of sunlight or heat to give you chlorine atoms. And in the chain propagation step, this chlorine atom meets an alkane and forms, takes an H, forms an ethyl radical and HCl. And this ethyl radical then reacts with a molecule of chlorine to form ethyl chloride and gives you chlorine atom, which keeps making the propagation steps happen. Now, here there is one important thing to be understood, and that is these photochemical reactions are zero order reactions. Now, zero order reactions by definitions are reactions where collisions don't happen. Because if collisions happen, then the reactions have to be having an order other than zero, because the rate will increase with concentration. More concentration means more collision, and more collision means faster reaction. A zero order reaction is a reaction where the rate is constant, meaning there is actually no collision taking place, because if it were to take place, higher concentration would lead to higher collision. But how can something react without collision? The answer to this is that here the rate determining step is this initiation step. It is this step which is the RDS. That means if I have, let's say, 1 million chlorine molecules and 1 million ethane molecules, I give 20 photons per second. So in 1 second, how many chlorine molecules do you think will break? 20. So how many chlorine atoms do you get? 40. So what are the chances that these 40 molecules will meet each other, or these 40 molecules will meet 1 million molecules of ethane? Obviously, chlorine atom will meet ethane more. If they meet themselves, they'll form chlorine molecule, but they are very small in number. So the chance of this chlorine atom meeting those ethanes are greater. But 40 chlorine atom will only meet 40 ethane molecules, right? So you get 40 ethyl radical. Now what will this 40 ethyl radical do? Will the 40 ethyl molecules meet each other? Will they meet some of the chlorine atoms found, which are also less in number? Or will it meet chlorine molecule, which is almost 1 million? It will meet a chlorine molecule. So when it meets a chlorine molecule, you'll find ethyl chloride formed. Now all these steps are the ones, all the propagation steps are the ones where collision is happening. But the RDS is the number of photons being given per second, or the amount of energy given per second, which is what is your rate constant in a zero order reaction K. Now, as the reaction keeps proceeding, there comes a time when ethane starts depleting, chlorine starts depleting, and there comes a time near the end of the reaction where chlorine atoms are sufficient in number to meet each other, where chlorine can meet an ethyl radical to form ethyl chloride. Well, two ethyl radicals can meet to form butane. But these are very low products. And remember, since this is a chain reaction, polyhalogenation is always a possibility. As I said in the beginning, you can't just stop it at one Cl. You will get a variety of this. But remember, you can get this in excess if you were to use this in excess. So that the chances of chlorine meeting an methyl chloride than a methane is far less if methane is very high. Similarly, you can get this in excess. All you have to do is keep chlorine is in excess. So that every time chlorine reacts with this and forms a monochloride, the rest of the chlorines have a higher tendency to meet this one. And therefore, you will get CCl4 in excess. So if CH4 is in excess, then the major product is CH2Cl. If Cl2 is in excess, the major product is CCl4. Now in the first propagation step, as you can see, this took an H. Now if this is formed instead of this. I mean, why didn't the carbon H bond break and carbon take the Cl and give the H atom? That is because the activation energy for this is much higher. Obviously, in this reaction, a primary isotopic effect is observed because the CH bond is breaking and CH4 reacts 12 times faster than CD4. And the reactivity of halogen is in this order because they are very reactive F dots. Now, the reactivity of alkyl radicals is decreased by adding radical inhibitors such as O2 or inert gas. Now, if you add O2 or inert gas, the chances of the reaction happening become less. Sometimes they are hindered, sometimes they are even stopped. If you simply add O2, what will happen is the pi bond of O breaks and there are two diradicals formed. One of them will react with the R dot and consume it and form a peroxide radical. Whereas if you add inert gas, it will slow down the reaction because more collisions of R dots and X dots will take place with noble gases, not leading to any reaction. So there will be no productive collisions. Now, halogens of higher alkanes other than methane, ethane can give you more than one product. What it means is, say for example, you have propane reacting with chlorine, you have an option of getting a primary and a secondary. Now, even though the mechanism is same for both, it is seen that chlorination and bromination, they differ a lot in the yield of the product. And this is the key to this reaction. This is what we are going to discuss in this reaction mainly. That one reactant having, let's say, two types of hydrogens, primary and tertiary. You do chlorination, you will get one type in major. But if you do bromination, you get the other type in major. And not only that, the extent to which each of them are major is also different. So we need to understand what is the difference between chlorination and bromination. Say for example, you have this. This is, as you can see, 2-methylpropane or isobutane reacting with chlorine molecule, H nu heat. You get a tertiary and you get a primary. The tertiary is 35.7% in yield and the primary is 64.3% in yield. That's fine. But when you do bromination, now look what happens. The tertiary bromo and a primary bromo, the tertiary is 99.44% while the primary is only 0.56%. Now this is a huge difference and this is what we need to understand. So what we're going to do is we're going to look at that important and key step of a reaction, of this chain reaction, which is responsible for this difference. When I say key step, I don't imply RDS. RDS only determines the rate. Key step is in the sense of which step is make or deciding the fate of which product is formed more. That is what we're going to discuss now. And we're going to see what the difference in chlorination and bromination for that particular step. So, to explain this, we need to understand the key step where this difference arises. The key step is the first chain propagation step. It is in this step that the halogen abstracts the hydrogen atom from the alkane, making it a radical. The nature of the radical formed depends on the nature of the hydrogen atom abstracted. So what we're going to do is we're going to say, okay, which is the step which is important? The first propagation step was the step in which there was an alkane, there was a halogen atom. The halogen atom took the H from the alkane, formed an alkyl radical and an HX. This is the key step. Why? Because which H it abstracts is the one that will decide which halogen will form. If it abstracts a primary H more, you'll get a primary product. If it abstracts a tertiary H more, you will get a tertiary product as major. So this is the key step. All right. Let's check some more. In the substrate, there are only two kinds of H present, primary and tertiary. So which product is major depends on the H atom that is abstracted by the halogen atom. Now let's look at chlorine. So you get a tertiary radical and HCl if it takes a tertiary H, or it may take a primary H and give you a primary radical. Now one can say, oh, all right, tertiary radical is more stable and therefore that should form more. Well, then why is it that the primary product is more in number than tertiary? And secondly, wouldn't this be same for both chlorination and bromination? Wouldn't they give the same value? If they did, then this is the reason that we would use. So there are three factors that affect the nature of H abstraction. First is called the probability factor. Now in the probability factor, what you need to understand is if you look at isobutane, there are 9 primary hydrogens and 1 tertiary hydrogen. So from the point of view of probability, if the halogen atom were to simply collide, which H is it likely to collide with more? Obviously the one which is greater in number, right? That is primary. In fact, it has a chance, 9 times chance of colliding with a primary than a tertiary because there are 9 primary H and 1 tertiary H. But then if this were the only factor, wouldn't it be same for chlorination and bromination again? So this is a factor important enough, but not the only factor, and they're definitely not the factor that explains the difference. Alright, so in isobutane there are 9 primary H atoms, well there is only 1 tertiary H atom. Therefore, there are 9 times more chances that a primary hydrogen is abstracted than a tertiary. But this factor would be same for both chlorination and bromination. Then comes the stability factor. Now this factor says which radical is more likely to form. Which is more stable radical, tertiary or primary? Obviously tertiary. So if this factor alone were responsible, I'll get tertiary product more. And not only that, wouldn't I get the same thing for chlorination and bromination? Because the radical in either case would be tertiary more stable than primary. So again, it is a factor of importance, but not the only factor. Or probably these two are not the only factors. And moreover, this cannot account for the difference between chlorination and bromination. So tertiary radical is more stable than a primary radical. This means that tertiary hydrogen is more reactive than a primary hydrogen. So obviously, the chances of a tertiary radical forming should be greater than that of the primary radical forming. This factor is again same for both chlorination and bromination. So it is the last factor which I think would be helpful, and that is called reactivity selectivity factor. Now it is found that the selectivity of chlorine atom to abstract the hydrogen atom is of the order of 5:3.8:1 for tertiary, secondary and primary, while the same for bromine is 1600:82:1. Now look at this. Chlorine has a higher chance of abstracting a tertiary H. 5 times more. 3.8 times more for secondary compared to primary. Whereas for bromine, it is 1600 times more than primary. The secondary, it's 82 times more than primary. How do we account for this huge difference? This is what we are about to see. So, if I look at this table and if I look at the hydrogen and the halogen, let's say this is tertiary, secondary, and primary, fluorine doesn't bother. It's 1, 1, 1. Its ability to take tertiary, secondary, primary is just equal. But for chlorine, it is 5 is to 3.8 is to 1. For bromine, it is 1600 is to 82 is to 1. Now, it is this difference that creates the variation in the product yield for both. And to understand this, we need to understand their bond energies. So bond energies play an important role. The bond energies are the ones that are going to determine everything in this. So just watch this part very, very closely. Remember, make notes, pause. If you want to think, write, and then proceed. So the primary CH bond energy is 98 kcal per mole. The secondary CH should be less because the radical is more stable, 95. The tertiary should be even lesser, 93. HCl is 103 kcal per mole, whereas HBr is 87. Now let's look at the key step again, and let's calculate its enthalpy change. So suppose this reacts with Cl dot and forms tertiary and HCl. Now tell me which bond is broken. The tertiary CH bond is broken. And remember, the tertiary CH bond requires 93 kcal and you have to give this energy. Which bond is formed? HCl. And how much is HCl? 103. It's going to release it, so it's going to be negative. So what do you think will be the delta H? The delta H is going to be negative 10. Okay. Let's look at the primary. So primary requires 98 to break. HCl will produce 103. So how much is net released? Negative 5. Well, let's see the same with bromine. Now again, tertiary is broken. Well, tertiary would need 93. But what is the energy of HBr? HBr is only 87. So this is required and only 87 is released. Can you see this is endothermic? And it is 6 kcal. What happens with primary? Primary radical is how much is to be required to be broken? 98. How much is formed? 87. Rather, it will be more positive. This will be even more positive. And therefore, this is negative, positive 11 kcal. So what you can see is that with chlorine, the key step is exo, while with bromine, it is endo, irrespective of the nature of H abstracted. So if we were to draw the energy profile for the key step in chlorination and bromination is that for chlorination, the energy profile goes like this. RH and Cl dot, R dot and HCl. For bromination, it is like this. RH for Br dot, R dot and HBr. Endothermic. Now in bromination, the transition state is closer to the product as the reaction is endothermic. This means that the transition state is more radical-like in bromination than in chlorination, and this is called the Hammond's postulate. This means the stability of the transition state of bromination will be more affected by the difference in the stability of the radicals formed than in chlorination. Very, very important to understand. Look at bromination. This transition state is closer to the radical. Look at chlorination. This is more closer to the reactant than the radical. So which transition state is more radical-like? Bromination. So don't you think the stability of radical will affect bromination transition state more than the chlorination transition state? It will affect both. In both cases, the transition state of tertiary will be lower. But if the transition state of tertiary is lower in both, but how much margin? Since bromination's TS is more affected by the stability, the difference will be more. Whereas in chlorination, it will be lesser. The tertiary will be lower than primary, but the difference will be lesser. So in chlorination, if you notice, I have this blue graph and a green graph. Now the blue is for tertiary H. Reactants are same. The green is for primary H. In fact, as you go along the x-axis, the difference between these points actually increase. Of course, the way I've drawn the graph, it doesn't suggest so. But remember, as it goes on the right axis, the difference between the blue graph and the corresponding red point will keep on increasing till it reaches a maxima here. Now, if this gap, the gap between the two radical is let's say 10 kcal, and the gap between the two TS, let's say the transition state of chlorination is only 20% radical like, don't you think this gap will only be 2 kcal? Whereas in bromination, if you look at this and this, the pink one is tertiary, the red one is primary. Can you see the TS is more radical like? So if the radical difference is 10 kcal, wouldn't the transition state difference be, if let's say if it is 80% radical like, wouldn't it be 8 kcal? So can you see bromination is more affected by the stability of the radical than chlorination is, even though in chlorination and bromination in both, tertiary is better. This is why bromine prefers tertiary H abstraction much more than chlorine does, even though both prefer tertiary. Now to calculate the percentage yield, we simply need to multiply the probability factor with the selectivity factor. So amount of tertiary Cl to the primary Cl will be, first look at the probability factor. Isn't the primary 9 times more than tertiary in terms of number of hydrogen atom? Whereas the selectivity factor for tertiary is 5 and primary is 1. So the value is 5 by 9. Now how much does this become a percentage? It's 5 by 14 and 9 by 14, which is exactly the value that you get. Whereas if you were to look at this for bromination, tertiary, primary, 1 by 9, 1600 is to 1. Now look at this ratio, 1600 by 9. Percentage of tertiary would be 1600 over 1609, which is 99.44, whereas for primary it's hardly anything. And this is exactly the values that we get. So remember, the major product of bromination is decided by the selectivity factor, while the major product of chlorination is decided both by the selectivity and probability factor. The major product of fluorination is decided only by the probability factor, as the selectivity factor for all of them is same. The next reaction is nitration, not a big deal. Nitration of the alkanes may be carried out in the presence of vapor phase between 150 to 475 degrees Celsius when a complex mixture of mononitroalkanes is obtained. So what basically happens is, you have an alkane, you add HNO3, it will start breaking the CH bonds and put NO2 there. It can even break the CC bonds and put NO2 there. You will get a variety and a mixture of compounds. None of them are actually going to be producing good yield. The mixture consists of all the possible mononitro derivatives and the nitro compounds formed by every possible chain fission of the alkane. For example, propane gives a mixture of 1 nitropropane, 2 nitropropane, nitroethane, nitromethane. Look at this. 1 nitropropane, 2 nitropropane, the CH bonds are broken. CC bonds are also broken, you get nitroethane and nitromethane. Nitration of alkanes follows free radical pathway, and reactivity of H is as usual, tertiary more than secondary more than primary, because it's a radical pathway. The cleavage of H is actually called the liquid phase nitration because it happens in liquid phase, while in vapor phase, CC bond is likely to break more easily. The next reaction again, which is not that much of a use, is sulphonation. Now sulphonation of alkane is done for hexane and higher homologues, since the radicals formed would be more stable. Mechanism is free radical. Reactivity of H is again tertiary, secondary and primary based on free radical. Exception to the first rule is isobutane, as it is having a tertiary H. So the first rule says hexane and higher, well, isobutane can do it. and therefore you have isobutane, you have sulfuric acid, and you're going to get tertiary H going, and that's it. That's about it. Then comes isomerization, which is of some use. Again, the mechanism is extremely weird in this. It's a process by which an alkane is converted into branched alkane containing a methyl group in the side chain by heating the N alkane with AlCl3 HCl at 300 degrees Celsius. Now, alkenes undergo isomerization should have a minimum of at least 4 carbons, because only then you can have chain isomers. Say for butane, if I have, I'll treat this with these reagents, I get isobutane. I take pentane, well, I get iso. And in fact, not only that, I can even get the neopentane. The mechanism of isomerization is based on carbocation formation, and I wouldn't really recommend you to, you know, uh, uh, go through this, because it's not actually required that much, and it's pretty weird. But I'm still going to show you. So AlCl3 first reacts with HCl to give you H plus and AlCl3 minus, AlCl4 minus. You have this. For some weird reason, the H plus takes an H minus and forms H2 gas, and you get a secondary carbocation, which is expected. So this carbocation is the best one that can form here. But now everything weird happens. The rearrangement of this carbocation occurs to create more stable carbocation, irrespective of whether stability is gained or lost in each step. It's never the case. This is rare and is observed only in isomerization reaction. So now let's look what happens. Secondary. Now generally you would not expect it to rearrange. But what happens is, this bond breaks. It's a primary carbon shift, and this shifts here. And you get this primary carbon shift. Then you have a hydride shift, and you get a tertiary. The same logic applies. Of course, it'll take some H minus and it will form alkane. Again, the same process continues. The H plus comes and forms a secondary radical here. Takes an H minus. Again, you will find secondary shift. To which secondary is going to shift? This will break and this will join here. Won't you get this? Then a hydride shift. You get this. Takes H minus. Forms this. Now, of course, there was always a possibility that instead of this shifting, I could have had, of course, from this, I could have had a methyl shift, and that would have given me this. And then this would have taken this. And you can see how weird these are. These are not the regular carbocation rearrangements. So even if you don't spend time in this, it's absolutely fine. But isomerization is actually used in the petroleum industry to create more branched alkanes to reduce their boiling points. The next reaction is pyrolysis, which you probably know by the word cracking. Pyrolysis is the fragmentation of an alkane into several individual components. It is used in the petroleum industry, also known as thermal fragmentation or cracking. In this process, the CC and the CH bonds break. All possible things break. You cannot do these in the lab and they're of no use, but they're useful in the industry. So when you do pyrolysis, let's say 2 carbon atoms give 2H, give the H2 and form an alkene. The CC bonds can break. You can get this, you can get this, you can get a variety of compound. It's free radical. We really don't have to do much in this. Then comes aromatization. Now in aromatization, this is the conversion of aliphatic compounds to aromatic compounds. Aromatization of N alkanes containing 6 or more, obviously you need 6 or more, into benzene and its homologues takes place at high temperature, 5 to 600, in the presence of Cr2O3 and Al2O3 as catalyst. So you have hexane. So what do you think will happen? Well, the 2 hydrogens from this will go away and the two carbons will join to form a cyclohexane ring. As you can see, it's a dehydrogenation reaction. So dehydrogenation takes place from all carbon atoms leading to benzene. What do you think will happen to heptane? Well, again, it will form a six-membered ring first. Then make it aromatic, you get a toluene. Okay. How about octane? Now, octane can join in two ways. These two can join and form a dimethylbenzene, a xylene, orthoxylene, or this could join here. This could join here, which means you get an ethylbenzene. The next one is oxidation. Now, oxidation has basically four ways of getting it done. You have complete oxidation. This is where you have direct reaction with oxygen, which we call as combustion. CnH2n plus 2 plus 3n plus 1 O2, and you get NCO2 and water. Now, the efficiency of this reaction is calculated as calorific value, which is the heat evolved per gram of fuel. So remember, when we use a fuel, it's not just about how well it performs. It's about how much energy can you get out of that per gram versus the amount of grams it is produced. So these are the two things in economics that one has to see before using something as a fuel. And if you want to find which has a higher calorific value, the one which has higher H to C ratio does have. Then you have incomplete combustion, oxidation. Not a big deal. We know this. Carbon is produced, and then you can even get carbon monoxide being produced. So you get everything. You have to learn these reactions. Then you have catalytic oxidation, methane O2 with red hot copper or iron tube. In the presence of high P and T, you will get methanol. Methane with O2 with molybdenum oxide as the catalyst, you will get formaldehyde and water. And methane with water, you get manganese acetate, and you're going to get formic acid. So just learn these reactions. There's no logic to it. And then comes chemical oxidation. The chemical oxidation is again pretty simple. Tertiary H is replaced by OH. That's as simple as that. Generally, alkanes are resistant to chemical oxidation, but if it has a tertiary carbon, then it undergoes oxidation in the presence of KMnO4 to tertiary alcohol. So KMnO4, tertiary alcohol. KMnO4, which alcohol do you think it will get? Look at the tertiary carbon. Obviously here. What about this? There are two tertiary carbons, 2 times OH. Now, in the end, we are going to do two important things which are basically there in your school syllabus, not probably in JEE. There is octane number and cetane number, and these have something to do with the petroleum industry. What we call as the knocking property and the anti-knock property. So next is the octane number. Now, octane number is used for gasoline and petrol fuel. It is a measure of anti-knocking property of an automobile fuel. Now, knocking in an internal combustion engine is a sharp sound caused by the premature combustion of part of the compressed air fuel mixture in the cylinder. So, it is premature combustion. Now, knocking can cause overheating of the spark plug points, erosion of the combustion chamber surface, and rough, inefficient operation. Now, it can be avoided by many ways. One, by adjusting certain variables of the engine design and operation, such as compression ratio and burning time. But the most common method is to burn gasoline of higher octane number. Remember, higher octane number implies lesser knocking property. The best compound is isooctane. It has the least knocking property or highest anti-knocking property. It's rated as 100. And the worst is heptane. It has the anti-knocking property of 0. So if a mixture is rated as octane number 90, it means it has the same knocking property as a mixture containing 90% isooctane and 10% heptane. So isooctane has the highest octane number of 100 and N-heptane has the lowest at 0. A fuel having octane number rating 90 has the same efficiency as a mixture of 90% isooctane and 10% N-heptane. Similarly, we have cetane number, which is used for diesel fuel. Cetane, which is undecane, has a cetane number of 100 and alpha methyl naphthalene has a cetane number of 0. Alpha methyl naphthalene is this. This is alpha methyl naphthalene. This is a cetane number of 0. And a diesel fuel with cetane rating of 90 has the same anti-knock property as a mixture of 90% cetane and 10% alpha methyl naphthalene. So with that, we come to the end of this video. So that's it for alkanes now. We're doing hydrocarbons. First part was alkanes. We have done alkanes completely. We've done everything in alkanes. The next part that we'll be doing would be alkenes. Alkenes will be done in 3 parts. First, we'll do the preparation, the introduction and preparation. Secondly, we'll do chemical and physical properties. Third would be a special alkene feature called dienes. So till I get to that video, have a nice day, study hard, watch this video as many times as you want, make notes properly, don't waste your time. And with that, this is Kalyan Kumar signing off. Have a nice and wonderful day and thank you for watching this.